Khazaei is an assistant professor in electrical and computer engineering department here at Lehigh University. He's also the director of Integrated Resilient and Intelligent Energy Systems Shortboard Integrity Lab at Lehigh University. Prior to joining Lehigh, he was an assistant professor at Penn State Harrisburg and affiliated assistant professor of Penn State University's Park Architectural Engineering Department. Dr. Khazaei obtained his PhD in electrical engineering from University of South Florida in 2016. And among his research interests are smart grid dynamics and control, data-driven model identification and controlling power systems, water energy microgrids, smart grid cybersecurity, and renewable energy integration into cyber-physical systems. Today, he will be talking about the fundamentals of microgrids and its models. And we are very grateful for having him because I know that this time of the semester is crazy. So thank you so much for agreeing to do this for our task committee. And just an FYI, this is designed for people who don't have that much of in-depth information and knowledge about power systems and microgrids. So if you are an electrical engineer and you know a lot about microgrid, many of this might be a review for you. So just be patient in that aspect. Thank you.
Thank you, Dr. Mohseni, for the introduction. I want to introduce again our three-part webinar. So the first one is the gentle introduction to power systems, which we have implemented on November 7, and you can all watch the first part on our YouTube channel using this link, and we will also share it in the chat so you can directly click on that link. And then today we're going to talk about the inside look at microgrids as Dr. Mohseni has introduced. And then the third one, we will have the simulation platform for power systems. So how we can directly model all the power systems. And this will be led by Panda Power and will be held on February 2nd, 2025 at 10 to 11:30 Eastern time. So please subscribe to our YouTube channel and also register to our task committee so you can get updates into this webinar series. We will later also have a webinar feedback where you can also let us know what's your preferences on next future webinar series and how we can evolve from this three-part webinar series. I think without further ado, Dr. K, please you can start the presentation. Thank you.
Thank you, Saskia. Hello, everyone. Good morning and good afternoon and evening all over the world. Thank you for having me. It's a pleasure to be here. I hope this introduction to microgrid will help some of you who are just new to microgrids and energy management and power system to learn something which you can utilize for your own research. So in today's talk, I'm going to first start with an introduction to microgrids, what they are, what are the main components of a microgrid, how to control a microgrid, and we will look into the energy management aspect of microgrid. And since the energy management is going to involve an optimization problem, for those of you who are not familiar with optimization, I will have a couple of slides explaining what linear and nonlinear optimization programmings are, how to develop a program in MATLAB as an example to solve these types of optimization problems. Then we will get into the details of two energy management problems that are common in microgrids. One of them is economic dispatch, which is the most commonly used approach for managing energy within microgrids. And the next one is the optimal power flow, which is mostly for larger scale microgrids, which are basically at the distribution level with many distribution lines and they are connected. So it would be utilized for network microgrids. And eventually I will give you a demo on MATLAB on how you would develop these kind of programs and run, and we'll show you some of the preliminary results that we have obtained. So a brief introduction to a microgrid. Some of you might have heard of it or might be familiar with it. Microgrid is a localized energy resource composed of many components that we call distributed energy resources, or DERs. The recent term for the DER has changed to IBRs, which stands for inverter-based resources. And those are nothing but wind farms, solar generation, battery storage system, and also conventional generation, fossil fuel-based generators, and so on. So this microgrid can be connected to the main grid or can operate in a standalone where the connection to the main grid is lost. And this is one of the main advantages of having a microgrid because it will provide resilience to the power system. So the main components, as I mentioned, would be distributed energy resources or DERs. Microgrid is going to have most of the microgrids right now in place have a centralized control unit, which basically manages the energy flow between resources and also ensures the stability of the whole system when it's connected to the main grid or when it's operating in the standalone or isolated mode. Loads are the most important components of a microgrid. The main purpose of having a microgrid is to provide energy support for the loads. Those loads can be categorized into the critical and non-critical categories, and this would depend on the context or depend on the situation where you install the microgrid. As an example, if you install a microgrid for a community of buildings or a community that has some industries and maybe hospitals, in those situations, the hospital is going to be the critical load and residential loads are going to be the non-critical ones because you must provide energy 24/7 to a hospital. Another point is when you connect the microgrid to the main grid, that point is called point of common coupling. So you're going to see PCC a lot used in my slides. So I just wanted to clarify that that's the point which we connect the microgrid to the main grid. And I'm going to have a couple of examples showing where the PCC is. So when it comes to different types of microgrids, we have first the most commonly used one is the AC microgrid, which is connected to the main AC grid. So this is identified by a node. So a node in a microgrid is called a bus. So we call it AC bus because if a microgrid is AC, its main node is going to be AC. AC means alternating current. So you use a point of common coupling to connect this whole microgrid, which is AC, to the main grid. And this is going to have multiple components. So you can have AC loads. These are the alternating current loads. For example, the buildings, hospitals, and everything that we consume in our houses are going to be AC because they consume alternating current. You might have some DC loads. For example, if you have an electric vehicle or EV charger in your house, then this charger operates on the DC or direct current. To be able to connect to the AC bus, you would need a converter, which is called DC to AC converter. Sometimes you hear the word inverter is used for this conversion. So this inverter means I'm converting DC to AC. You can also have some resources or power generating units such as renewable generation. As an example, a photovoltaic system or PV system produces or utilizes a DC or direct current. Then if you want to connect it to the main bus, which is operating on AC, you would need to convert that from DC to AC. So you can see a lot of converters used in microgrids. This is mainly to allow connection of different or various resources to the main node. In this case, this is the structure of an AC microgrid. Next one is a DC microgrid, which is mostly used in different applications such as airplanes, Navy ships, and so on. So this is structure. The main bus is going to be DC, and you're going to have a main converter, which is going to convert your DC to AC so that you can enable connection to the main grid because the main grid operates on AC. And this DC microgrid can have AC loads. So if you have AC loads, then you would have converters that would convert this AC to DC so that you can connect to the main DC bus. You can also directly connect your DC sources to your DC bus. Here you would use a DC to DC converter, mainly to control the charging and discharging of your electric vehicle. And if you have renewable energy sources, then you would utilize DC to DC converters or AC to DC converters, basically to allow control of your renewable generation. So this is the structure of a DC microgrid. Next one is a hybrid DC-AC microgrid. So as the name shows, you're going to have two nodes. So you're going to have both AC and DC buses in your system. And to connect to the main grid, you would have a point of common coupling that would connect these two buses. For the DC bus, you would need to have a converter that converts your DC to AC so that it allows connection to the main AC point of common coupling. In each network, so you're going to have AC network and DC network. In each of those, you can have both DC and AC components. Here, for example, we are just showing only the AC components. the AC loads can directly connect to the AC node, and if you have renewable energy source, you can also connect to the main bus. And these are going to be converters that are utilized for example, wind turbines. You have two converters that are connected back to back. It converts first AC to DC and then DC to AC so that you connect to the AC node. And this allows the control of this wind turbine. And similarly, you can have some DC loads and DC renewable generation directly connected to the main bus. So this is the structure of a hybrid DC-AC microgrid. Now we're moving on to the control. So now that we know we have different configurations of a microgrid, what are the control designs that we are interested in or we have right now in practice? So a control of a microgrid is going to have multiple layers. We call it hierarchical control framework. As you can see, it has primary control, secondary control, and tertiary control. The primary control is in charge of controlling the voltage and currents and also the power, active and reactive powers that you basically get out of a device within a microgrid. And this is a very fast control, meaning it's going to happen in a few milliseconds or in a couple of milliseconds. Then you have the secondary control, which is basically trying to synchronize your components to the main grid or compensate the mismatch between the voltage and frequency that your DER or inverter-based resource is causing when it's connected to the main grid. So the secondary control is going to compensate for that. And I have examples to show what these controllers are. So this is usually 10 to 15 times faster than the primary controller. Again, you're looking at tens or hundreds of milliseconds for these two controllers. And these two controllers are at the local level. That means if you buy an inverter-based resource off the shelf, it already comes with these two controllers implemented. And what you would do is basically you can control at the tertiary level. So that would be basically the set points that you would set to this converter or this distributed energy resource to control the amount of active and reactive power that you're getting from this unit. And this is the level that we are going to focus on today. And we are not going to get into the control design for the local level because this mostly is going to be a control problem. But here, the tertiary control is going to be the energy management problem, which would lead to our economic dispatch and optimal power flow, which I'm going to discuss today. So let's take a look at these control loops briefly. Here you see a structure of a microgrid. This is your point of common coupling. And the orange boxes are basically the primary controllers. Here you see two different DERs, but both of them have the same primary control implemented. Here, the first box over here is your inverter, or basically the resource, the DER. And these are the control loops. So you have a current control to basically control the amount of current that is going out of this device. And this is mostly for protection against overcurrents or against faults. And then you have the voltage control, which is going to control the voltage that you have in the output of your device. And then on top of that, you have a controller, which is called active and reactive or PQ controller. Sometimes you hear droop control utilized for this control. And this is going to control the amount of active and reactive power that you're sending out from this device. So this is the structure of the primary control. And when it comes to the secondary control, what you do is you take a look at the voltage and the voltage magnitude and frequency right at the point of common coupling. For example, if you want your microgrid to operate at 110 volts, then this voltage must be 110 volts. As a result of primary control, sometimes you might not get 110 volts, you might get 100 volts. So in this case, you have to compensate the mismatch between what you're expecting and what this device is basically giving you. So in those cases, you take a look at the deviations of the frequency and deviations of the voltage. You design a controller, which is called secondary control, and that is going to compensate for the mismatch that you see at the point of common coupling. So this structure is called the secondary control. So again, these are the local level, which we are not going to get into the details. Usually the control classes and graduate level classes are the ones that we cover the aspect of control design for these two loops. Now we get into the tertiary control framework, which is mostly related to the energy management in a microgrid. So if you have this microgrid with the secondary control, which you just saw in the previous slide, the main component for the secondary control, as you can see, is the reference of the frequency and voltage. So these are the inputs to the secondary control. So the controller that provides this input is going to be called the tertiary control. This is usually at the grid level so that you can come up with the references of active and reactive power that you want to draw from each resource within a microgrid. So For example, if you have a power consumption within a microgrid, you come up with a program that basically tells you how much active and reactive power each resource within your microgrid should provide. So this is the energy management part where we will look into more details. So within the tertiary control, we have two frameworks that we are going to utilize. One is economic dispatch. So as you remember, we are going to find the active and reactive power references that we send to the controller of each unit or each DER within a microgrid. And to find these active and reactive powers, we solve a program which is called economic dispatch. This means I want to minimize the overall cost of running this microgrid because I have many resources, and for each resource, I'm paying a cost. So if I'm running this microgrid as an example, I have to buy fuel so that I can run my conventional generator units. Or if I'm, for example, using energy storage or solar or even wind, I have to pay for the operation and maintenance of these devices. So there's a cost associated with running this microgrid and every unit within the microgrid. So what I want to do is I want to minimize the overall cost of running this microgrid at any time, given that my main condition is that I want to make sure all these resources, if I add up the power that I'm getting from all of these resources, that should be exactly the same as the amount of power that I'm consuming within the microgrid. So this is called the power balance. That means your generation should match the demand. And there are going to be some constraints within the system. For example, you can't just provide as if your battery is empty, you can't utilize the battery, right? So these are some of the constraints which I'm going to explain later on. But this type of problem is called economic dispatch. And as you can see, this problem involves solving an optimization problem. And usually you do that within either close to real time, which we call it every 3 to 5 minutes, or even faster within a microgrid. So at the grid level, we are running it at every 3 to 5 minutes because this problem is large. We have millions of, for example, resources that we can utilize. But at the microgrid level, you have only a few resources. You can run this problem much faster. This optimization is not going to be complex to solve. You are going to have real-time economic dispatch, which would be close to real-time, or you can run it on an hourly basis. So every hour you would run this problem and find out which of these resources should be on for your system. So since this problem involves solving an optimization, I decided to add a few slides explaining what a linear programming or what a nonlinear programming optimizations are, and teach you how to solve these problems using MATLAB. So LP is a linear optimization problem that involves solving an optimization with linear constraints and linear objective functions. So each optimization is going to have an objective function. For example, I'm minimizing the cost, and this cost is a linear function of my decision variables. In this case, would be the amount of power that I'm getting from each DER, and subject to some constraints. So the first one is called inequality constraint. Then I have an equality constraint, and I have some bounds. LB and UB, those are lower and upper bounds for each decision variable. So a couple of things to note. First of all, this is the expanded version of the same problem. Here, the problem number 1 is written in matrix form, and here you can see the expanded version of the same thing. So with regards to optimization, there are a couple of things that we need to know. The first one is the solution of this optimization, or we call it optimal solution, which is going to be the minimum value of the objective function f. Feasible solution is a solution that satisfies all these constraints, which is written close to the subject to line. So this means these are all my constraints of the optimization. If I have a solution that meets all of these conditions, this is called a feasible solution. And then we have an infeasible solution if at least one of these constraints are violated. And actually, we have a feasible. Sometimes we have multiple points, or we have a region that would represent all the possible points that would satisfy these conditions. In those cases, we call it a feasible region. And sometimes you have a maximization problem, so you can easily convert a maximization problem to a minimization problem by just multiplying the objective function by a -1. So this is just the introduction to an LP, which is a linear programming optimization. This is just an example. I wanted to show you how you could convert, for example, this problem from the expanded version to a matrix form. As you can see, I'm maximizing 3x1 plus x2. Here you can easily convert this to a matrix form in form of minimizing or maximizing c times x, where c is going to be 3 and 5 times your x, which is a vector of x1 and x2. And then here you have some inequalities. As you can see, all of these are less than or equal. So this is called an inequality. And you can convert it to a matrix form. As an example, the first row corresponds to the first one. This is 1x1 plus 0x2. So that's why you have 1 and 0. This is 0x1 plus 2x2. That's why you have 0 and 2. And then on the right-hand side, you have 4, 12, and 18. So that's how you would convert this problem to a matrix form, because MATLAB uses matrix form to solve this problem. Therefore, you have to first convert your problem to a matrix form. And you don't see any equality constraint. That's why AEQ and BEQ are 0. And then here you have your upper and lower bounds, because x1 and x2 are both positive. So they're going to be from 0 to infinity. And that's what you have for your upper and lower bounds. Now, I want to show you how you would graphically first solve this problem and show you a program that you can utilize in MATLAB. So if you're solving this kind of problem, you would need to first look at the feasible region, because the optimal solution of this problem exists or is in the feasible region. So take a look at this example. I have these constraints. The first one says x1 less than or equal to 4. So if you draw a line of here, your x-axis is x1 and your y-axis is x2. So if you're looking at x1 less than 4, so you draw a line x1 equals to 4, anything on the left side of this line is going to be less than 4. Or another one, you have 2x2 less than or equal to 12. If you draw a line 2x2 equals 12, that would be x2 equals 6. So anything underneath this line would be x2 less than 12. So you're basically looking at x1 and x2 positive. That would be the positive area here. And then the next one is 3x1 plus 2x2 less than or equal 18. So if you draw a line of 3x1 plus 2x2 equals 18, anything underneath the line is going to be less than 18. Then you have come up with the feasible region, which would be the intersection of all of these constraints or all of these areas. So this feasible region is going to be the region that your optimal response is going to exist. So if your optimal solution is beyond this region, then this solution is going to be infeasible. Now, to find your optimal solution graphically, what you can do is you can assign values to this maximization. First of all, you want to maximize this objective function. First, for example, give a value. For example, 10. If this 3x1 plus 5x2 is 10, this corresponds to this line. And then you can test and see if you can go higher, because you want to maximize this. So you can go up to 20, still in the feasible region. You can go up, and you can go up until getting to this point, which is 36. If you go a little bit up beyond this point, then you will be out of the feasible region and your solution is going to be infeasible. So this is one of the ways that you can graphically solve for this problem. That means at this point, you have found your optimal solution, which would be 36. And this is also good to know that the optimal solution of an optimization always exists in the edges of your feasible region. So any one of these 5 edges would correspond to your feasible or your optimal solution, which in this case was 2 and 6. So this is how you would implement something like this in MATLAB as an example. So MATLAB uses len_prog function to solve linear programming problems. The way that you set up the problem is written here. So there's a len_prog function that you will utilize. F is going to be basically the value of C in this case, which would be C times X. So in here, that's going to be the matrix that multiplies to the decision variable. So that would be, in my case, -3 and -5. If you remember, I'm maximizing this objective function. And if you have a maximization problem, that's similar to the min of minus fx. And MATLAB solves minimization. So in this case, you have to multiply it by a -1. So -3 -5 would be your objective function. And then I have defined A, B. I didn't have any equality constraints, so I left them empty. That means I don't have any equality in that problem. Lower bound 0, upper bound infinity for two decision variables. So if you run this program, this is going to give you the optimal value of x, and also the f value, which was going to be the optimal solution, which would be the minimum value of that function. Exit flag is something that you should check every time you run it, because if it's 1, that means you have found a feasible solution. If it gives you 2, then that means the solution has been infeasible, and that's what you have to go back and check and see why this has happened. So this is one example showing how you would solve linear programming using MATLAB. There's another toolbox that you can utilize, which links to MATLAB, and you can use, which is called OPTI. So this toolbox can be downloaded from this link that I provided here. I like this more than the optimization toolbox in MATLAB, mostly because it has more solvers to choose. And also it's more straightforward to implement. You can implement nonlinear programs. You can do mixed integer linear, mixed integer nonlinear programming, and you can solve different types of problems with this toolbox. Another cool feature about this toolbox is that it provides you a way to plot your feasible region and basically graphically take a look at the available feasible or your feasible region, which is a nice feature to have, and you don't have it in the MATLAB optimization. The format that you write it is almost identical to MATLAB. As an example, you can see that here I have defined F, A, B, A, Q, B, Q, upper and lower bound. The only difference is that here you have to create an OPTI object first, and that object, the format that you explain to this toolbox, how to format the problem is going to be a little bit different. Here you first define the objective function, then inequalities A and B, and then bounds are going to be lower bound and upper bound. So you don't have to follow exactly the same format as lane prog. Here you will use a different formatting, and then eventually just solve this OPTI object. And this is going to give you the same result that I just showed you in the previous slide. So this is another way of solving this optimization problem using a toolbox called OPTI. You can also use the same toolbox to solve nonlinear programs. We call them NLP. So the difference between NLP and LP is that in this case, your objective function or constraints can be nonlinear. So in this case, you can see that I have a nonlinear objective function, and also I can have nonlinear inequalities and nonlinear equality constraints added to my optimization. As an example, if you're solving this problem, your objective function is nonlinear. Here, the way that you define it in the program is that you define a function which is a function of x. So that @ sign x means this is a function of x. And then you just define it as x1 times x4 times x1 plus x2 plus x3 and plus x3. So that's how you would define the objective function. For the nonlinear constraints, the way that it works is that you have to define all your nonlinear constraints and provide a lower and upper bound for them. As an example, here I have x1, x2, x3, x4 more than or equal to 25. So its lower bound is 25 and its upper bound is infinity. That's why you see I have defined the lower bound as 25 and infinity for the first nonlinear constraint. For the second one, which is equality, then upper and lower bound would be 40. So here you can see that I have defined upper and lower bounds of this problem as 40, and then this is the nonlinear constraint. The rest is similar to the way that we wrote for the linear program. Just define the OPTI object function, and then you just solve this problem given the nonlinear constraints, upper and lower bounds of the nonlinear constraints, your objective function, and eventually solve this problem, and this gives you the optimal solution. So this was just a brief introduction to linear and nonlinear programming and how you would solve it in MATLAB. There are other toolboxes that you can use. One disadvantage of utilizing this form is that you have to convert some of your constraints to the matrix form and find A, B, AEQ, and BEQ. In these situations, that's if your system is large, this might be a little bit challenging. In these cases, what you can do is you can use other software such as GAMS or CVX. Those are the tools that you can directly write the optimization problem, but the approach is going to be the same. Now we can go back to the economic dispatch problem for the microgrid. So this problem, I have written it in a simplified version, and then later on we will add more details to it. So the objective is to minimize the cost of running the microgrid, and cost of running a microgrid would be cost of or minimizing the cost of running every resource in my system. So CIPI is basically cost of running every generation or every DR that I have within the microgrid. My main constraint is that I want to make sure that summation of all the powers that I'm generating, that would be sum of PI, should be the same as P load, should be the amount of power that I'm consuming within the microgrid. This is called power balance. You might have other system constraints, and the other one is that your powers of each resource are bounded between minimum and maximum. So this is the most simple way of running or formulating economic dispatch problem. Let's see how we can solve it. Within microgrid, I can have different resources. If it's conventional generator, I can have, for example, a combined heat and power or CHP generation. I can have natural gas. I can have diesel generators. So all of these are going to be categorized into conventional generator. So if you have a conventional generator, we have to first look at the cost function because we are minimizing the cost of running these units. The cost function for a conventional generation is a quadratic function, as you can see. A, B, C, those are cost coefficients. So those are going to be known depending on the type of generation unit. PI is the amount of power that you're getting from this unit. And here you can see the cost curve. So first of all, each unit is going to have minimum and maximum power. That means, for example, if you have a 6 megawatt combined heat and power generation, that means its maximum power is 6 megawatt and its minimum power is 0. So it's going to give you something between 0 and 6 megawatts. Sometimes you can't just turn on a generator basically you have to have a minimum amount so that you can run it. For example, for a 6 megawatt generator, it might not be economic to run it at 1, for example, megawatt. You must run it at least at 2 megawatt to generate some revenue for this device. In that case, you are going to have a P min, which is not going to be 0. So looking at this curve, this is a quadratic curve that shows that is shown here. What this means is that the more power you draw from this conventional generator, the more money or the more cost you're going to pay for buying the fuel, as an example. So this is the cost function. And then we have some constraints for running a conventional generators. The first one is the power bounds. So the power that you're generating within this conventional generator is going to be between minimum and maximum. So that's PG min and PG max. And you also have a status on and off. So the generator can be on or off at any moment. If it's on, this binary variable UDG is going to be 1. And if it's off, it's going to be 0. So this is a binary variable that shows if the generator is on or off. And then you have a ramp up and ramp down constraints. So what does that mean? That means, for example, you can't just within for example, within a couple of seconds, you can't just ramp up a generator and generate power, for example, from 0 to 6 megawatts. It's impossible because generator is a mechanical device. If you want to ramp it up, if you want to increase its power consumption, you have to rotate its rotor faster. So if you want to do that, this is a mechanical process. It's going to take time so that you can provide the energy that is needed to get to the speed that gives you more power. So in those cases, you have a limit of ramp up and ramp down. For example, you can't just increase it from 1 megawatt to 6 megawatt. You have to do it step by step at the steps of, for example, 30 kilowatts or steps of 50 kilowatts. So that's called the ramp up and ramp down maximum. So these two constraints define the ramp up and ramp down. And then you also have a startup and shutdown binary variable. So this means these two variables, first of all, are binary, meaning they're either 0 or 1. And this is how you would define it. You would look at the status of the unit at time t and at one time before that. So if this variable is 1, that means you have turned on the machine. And the status of is going to change from 0 to 1. So this is utilized for the cost because every time that you bring on a conventional generator, then you have to pay cost for that. So this is called a startup cost or shutdown cost. So we monitor this variable later on in the objective function. We incur a cost so that we can pay for the cost of starting up or shutting down this unit. So these constraints are for the conventional generation units. Then let's take a look at renewable energy resources. The first one is solar. So if you're looking at a solar generation, its cost is a linear function of the amount of power that you're extracting from this unit. For example, the more power you extract, the more money you have to pay to buy power from a solar, for example, producer. And this is a linear. KPV is just a cost coefficient which corresponds to the operation and maintenance costs of running this PV system. And then there are some constraints within the PV system. The first one is that your power that you can extract from a solar panel or a solar array is always between 0 and its maximum. The maximum depends on the amount of solar radiation that you get and the temperature of basically the panel. So this maximum power is decided by this equation. So this tells you the nominal power in a standard temperature condition or STC. And then this GAC is the solar radiation at time t. GSTC is the standard temperature condition for solar radiation. TC is your basically reference temperature, and TI is your current temperature. For example, if this is your current temperature profile over the 24 hours during the day, and this is your solar radiation over 24 hours in a day. If you put these two into this equation, this is the output of the solar panel power that you're getting. So this is the maximum available power that you can get from the solar. And you have to bound the amount of power that you're getting from the solar between 0 and this maximum available power. In the past, we would extract the maximum power, but now we have control over the solar panels so that we don't necessarily need to get the maximum power. Sometimes we utilize some portion of this power for the economic dispatch for running the loads, and the rest will be utilized, for example, to charge the batteries within the system or charge the electric vehicles. And then this is how we model renewable energy resources. For example, wind. The cost function is similar to the solar. It's a linear function of the amount of power that you get from the wind, and Kw is the cost coefficient of the wind turbine. Again, your wind turbine power is going to be between 0 and its maximum available power, and the maximum available power of a wind turbine depends on the wind speed. Here, this is the amount of power that you can get from a wind farm or a wind turbine from at different wind speeds. So here, Vt is the wind speed at time t. So if your wind speed is less than Vi, which is the cut in, or more than Vo, Vo is cut out. So that means if your wind speed is too small, for example, at 2 meters per second, you can't generate any power. Or if if outside is too windy, it's not safe to run the turbine. In those cases, you just shut down the unit so that it doesn't generate anything. And if your wind speed is between the nominal wind speed, so there is a nominal wind speed, for example, 10 meters per second, that you can get maximum power from a wind turbine. So if your wind speed is less than the nominal and more than the cut-in speed, for example, 2 meters per second, then you get a fraction of the nominal power of the wind turbine. And if your wind speed is more than the nominal and less than the cutout, which is going to be too dangerous to run, then you can get the maximum power from the wind turbine. So this is how you would basically calculate the output power of a wind turbine. I have an example that shows you how you would do something like that in MATLAB as an example. So for generating the wind turbine maximum power, you first need to take a look at the wind speed. Here you can look at the weather station and the wind speed around the wind farm that you're looking at. Or here, as an example, you see 24 values of wind speeds that we have collected from one of the stations at Penn State. For a nominal wind turbine of 100 megawatt with cut-in speed of 6, cut-out of 12, and the nominal wind speed of 10. So this is the MATLAB program that you just insert the time, the wind speed, and also the cut-in, cut-out, and nominal speeds. And this is basically an if-else condition that we have written for here. So if the wind speed is less than Vi or more than Vo, then it's 0. If it's between the nominal and Vo, it's just a fraction of the nominal, and otherwise it's going to be the nominal. So this shows the results. This is the wind speed, and here you can take a look at the output power of the wind farm. This is the maximum available power that you can get from the wind farm. Next one is the battery storage system. Similar to the PV and also wind, the cost function of the battery storage is also a linear function of its power consumption. And there are some constraints with regard to the battery. We can have different types of storage system within a microgrid. In this specific case, I'm mostly looking at the battery energy storage system, or we call it BESS. So one of the constraints is that the active power of the battery should be between minimum and maximum. The energy of the battery is its previous energy minus the efficiency. So that's the round trip efficiency of the battery, which tells you how much efficiency you're having for charging and discharging the battery. So times the power that you're getting from the battery, and your energy of the battery should be between minimum and maximum. So these are the constraints that you need to put to your optimization problem if you're running a battery storage into your system. And this is for one unit. If you have multiple batteries, then that means you need to have multiple versions of the same constraints for each energy storage in your system. So next is the load profile. So to run the economic dispatch, you have to basically take a look at the prediction of the energy consumption within your microgrid. Here, the microgrid is mostly having a electrical load, but later on, if you're working on, for example, water systems or buildings, you can add more dynamics and more details of different type of energy consuming devices within your microgrid. Here, I just have a 24-hour profile of a residential energy consumption or a residential building. I'm utilizing that as my load for the microgrid. Let's see how we would solve such a problem manually. So looking at the economic dispatch, which is written here, I'm minimizing the cost, given that I want to make sure the power balance is met, and I have some constraint to make sure my powers are bounded between minimum and maximum. So if you want to solve this problem, we use a method of Lagrange multipliers. The way it works is that you first form the Lagrange function, which is your cost function, plus this phi, which is sum of pi minus p load. So you multiply it by a Lagrange multiplier called lambda. So to minimize the Lagrange function, you just take a derivative of this function over your variables, which would be decision variables would be pi's, the amount of power that you're generating within each DR, and also your multiplier lambda. So if you solve this system of equations, then you will find your optimal response, which would be the PI's, power of resources, and you then check and see if they are within the bounds. If they're within the bounds, then you have solved this problem manually. So as you can see, this is a simplified version of the same problem. In reality, your problem is going to look like this. You're going to have objective function. You're going to have some equality constraint. You also are going to have some inequality constraints. So in the previous version, we didn't consider any of those, and we only considered equality constraints. So if your optimization has inequality constraints, you have to look at a systematic way of solving this problem, which is called the KKT condition. So that's Karush-Kahn-Tucker condition. Most famous way of solving this optimization, similar to the previous way, you just look at the Lagrange function, which is your cost function, plus Lagrange multiplier lambda times your equality constraints, and then you define a new variable called mu times your inequality constraints. So, and then you check these conditions. First is that you take the derivative similar to the previous way, take the derivative of the Lagrange function over every decision variable equal to 0. You solve system of equations, and you also need to make sure that gi of x is 0, and then j of x is less than or equal to 0. This is called primal feasibility. And then you have to check these two conditions, which are called dual feasibility, such that mu that you have defined here must be positive, and the complementary slackness means mu times h of j must be 0. So you will have system of equations and some conditions to check. By looking at all of these and solving those, you have found your optimal solution. But again, the purpose of this talk is not teach you how to solve this problem manually. So if you're more interested in learning how to do so, there are some courses within, for example, industrial engineering that you can take and learn more. But here we're just going to use a software to solve this program. So here I have a simple example which we're going to solve in MATLAB. So let's say I have 3 conventional generation units which are supporting a load. In this case, these are the cost functions of different resources. You see for generator 1, generator 2, generator 3, these are the quadratic cost functions that we mentioned. These are the minimum and maximum available powers that we can get from each resource. And this is the optimization problem. I want to minimize the cost of running all of these units such that the power that I'm getting in the load is going to be met by P1 plus P2 plus P3. And those are all bounded within minimum and maximum. So let's take a look and see how we would solve this problem in MATLAB. So I'm using OPTI toolbox again. I have defined the objective function, which would be the sum of all the cost coefficients of the units. So these are the quadratic functions, just add them up. I don't have any nonlinear constraints. I have one equality constraint, which tells me P1 plus P2 plus P3 equals P load, and this is P1 plus P2 plus P3 equals 850. 850 is my power consumption. And then lower bound and upper bounds of the units defined here. For the OPTI, you have to come up with an initial guess. You can randomly come up with a guess, and this problem is going to be solved. So formulating that, and you just get your solution using the OPTI toolbox. So this is the simple way of solving economic dispatch using MATLAB. But in practice, and if you run that, this is what you will find out. So your P1 is going to be 393. P2 334, and the P3 is going to be 122, and summation of this would be the load. So that tells you how much each generation unit should contribute so that you minimize the overall cost of running this system. So in practice, we have more constraints. We ignored system constraints in this case. Now we want to add all of those. So let's see what those are. Those are going to be the constraints of conventional generation, renewable energy constraints, and battery storage constraints. So in this case, I want to add more components to my microgrid. So let's take a look at the overall objective function for a complex economic dispatch. Here, I'm going to have the cost of running conventional generation units. Remember, I told you that for starting up and shutting down a unit, we have to pay a cost. So here, C up is the cost coefficient for starting up a conventional generation, and C down is the cost that you need to pay for shutting down a unit. So these are binary variables, and C is just the cost in dollar that you have to pay. For renewable generation, you have a cost of solar photovoltaic or PV, cost of wind, and cost of battery added to your objective function. Your load balance now is more complex. It's going to be sum of all the conventional generation plus sum of all the PV sources, wind, and battery. Sum of all the generation should be the same as sum of your load. And then we are going to have more constraints for conventional generation, renewable constraints, and battery storage. For example, we had the ramp up and ramp down constraints for the conventional generation. For the renewable sources, we had the min and max power of the resources. And for the battery, we had the energy constraints. So those have to be added to this problem. So this is for a microgrid which is islanded. That means there is no connection to the main grid. This microgrid is operating standalone. When you connect the microgrid to the main grid, you have to add some constraints. And the grid is going to impose two constraints. One is the cost of purchasing the power from the grid. So you can either buy the power from the grid or sell the power to the grid. So if P grid is positive, that means you're buying from the grid. So as an example, if P grid is positive, then C cell and this C cell is going to be canceled out. If P grid is negative, this is going to be positive, and here C buy and C buy is going to be canceled out, so that you can have either C buy times P grid if it's positive, and you're going to have C cell or minus C cell times P grid if it's negative. So here you can buy or sell power from the grid, and P grid is going to be a decision variable that you solve in optimization. The rest is similar to what we had before. On the load side, you can also have some cost functions. For example, if you have a chiller in your building or in a microgrid, that can cause cost to your system, you can add the cost of running a chiller. Or if you have pumps in water system that would consume energy, you can add the cost of running water pumps into your optimization problem. So this was the structure for developing the economic dispatch for islanded and also grid-connected microgrid. One thing that we didn't consider was, okay, what if your microgrid has multiple nodes and it's not just everything connected to the point of common coupling? So in those cases, when you have multi-node microgrids, you have to formulate the problem differently, and this is called optimal power flow, because you have to account for the amount of losses that you have within the transmission lines connecting different nodes within the microgrid. So this is not just single node microgrid now, it has become a multi-node microgrid. Before we define the optimal flow for this problem, I would need to briefly discuss the concepts of phasor. I think the previous speaker talked about phasors and power flow in power system in the previous webinar. So I'm going to briefly go over those again. So here we're looking at complex variables. So a phasor means a complex number that has magnitude and angle. You can write it in terms of a complex number. That's why you can see it has a real part and imaginary part. So in this case, all our currents and voltages within different nodes in the system are going to be complex numbers. And we have a complex power, which means I'm going to have active and reactive power, which is simply voltage times conjugate of the current, and both of these are phasors. We also need to look at the impedance of the line. So each transmission line is going to have, or each distribution line is going to have an impedance, which is defined as R plus J times X. And also the inverse of this impedance called admittance, that's called Y. So here, if you look at the complex power, we have to consider this as one of the constraints of the optimization. So that's the whole point. That's the main difference between economic dispatch and optimal flow, and that's what you will add to the optimization. So to simplify the problem, we found the relationship between the voltages at different nodes in the system. So that's the voltage at every node, and the currents that you're injecting at each node. So current injection means the amount of current that you're injecting using your resources and the amount of current that you're consuming in your load. So this is called the single line diagram. The circles show the generation and the arrows show basically the power consumption units. So this is a relationship between the current injection at each node and voltage injection, and this matrix itself is called the Y bus or bus admittance matrix. And the way that you find it is that for the diagonal entries of this matrix, you just sum up all the admittances. For example, if you look at node number 1, there are two admittances, Y12 and Y13. If you want to find the diagonal entry number 1, that's going to be Y12 plus Y13. And for the off diagonal elements, for example, Y12 is going to be negative of this admittance. So here you can see negative of Y12, and that's how you will form this. And this is going to depend on the topology of your microgrid. So once you find this relationship, you can simply write the current injection in as Y bus, which is this matrix, times the node injection, and you replace this into the complex power, and you simplify the real and imaginary parts. You come up with these two constraints. So this is called the active power constraint, and this is called the reactive power constraint. These two constraints would account for your losses within the lines in a multi-node microgrid, and that should be added to your economic dispatch. So now we can formulate the problem. The objective function is similar to what we have done before. We also have basically the optimal flow constraint, which is going to be the amount of active and reactive power that we have found in the previous slide. So that has to be added to the constraints. And since we are adding two decision variables, that would be reactive power and voltages. So for the voltages, since this is a phasor, we are going to have magnitude and angle of the voltage. And for all of these, we have to add the bounds to the optimization problem. Now, if you want to simplify the problem even further, this is how you formulate the optimal flow. The objective function is similar to what we had before. So you have bounds of active and reactive power. And this constraint, which was the complex power, now can be further simplified to the active power constraint and reactive power constraint. Here you can see everything is written in terms of magnitude and angle of the voltages and bus admittance matrix. So these two constraints are nonlinear constraints that are called power flow constraints, and those will be added to the optimization. So here I have a brief demo. I think I have only a couple of slides left, so I'm going to briefly go over the demo and show you a way that we can solve this problem in MATLAB. I have two models. You can see the model on the left side is just a single node microgrid. Since you don't have any lines to lose power, then in this case, you can run the economic dispatch problem. And for the multi-node microgrid, as you can see here, we will solve the optimal flow. For each of the resources, for each microgrid that we have multiple solar photovoltaic, battery storage system, and different conventional generation, combined heat and power, natural gas, and then we can have wind turbines. And those are the parameters of the system are given here as well. I think the slides have been shared with all of you. But looking at the economic dispatch problem, this is the full version of this model. I'm minimizing the cost. And these are basically the constraints of conventional generation, constraints of battery storage devices, constraints of wind and solar photovoltaic. And the last one is the load balance constraint. So I have to solve and formulate this problem. For the optimal flow, I have the objective function, which is written here, constraints of the conventional generation, constraints of the battery storage, solar photovoltaic. We have the constraints of basically active and reactive power consumption, and also the active voltage angle and voltage magnitude. And the last two constraints are the nonlinear ones for the power flow. So this one is the power flow model. As you can see, it's almost identical to economic dispatch, except the fact that we have replaced the power balance, which was this last constraint, with the power flow constraints. So we are going to have two more nonlinear constraints here. So now I want to show you basically a demo in MATLAB. First of all, you can find a full report of what I have explained here in a paper that Saskia actually published recently in arXiv. This is basically detailed version of what I explained today. The source codes are also available through this link. You can feel free to just download the MATLAB codes, but you need to install OPTI toolbox to do so. And also you can read more about the microeconomic dispatch through these papers. But I want to take a couple of minutes to talk about basically this MATLAB code if I have some time. Can I get 5 minutes to talk about this?
Yes.
So I will briefly show everybody, for example, the economic dispatch, and then I will go over the optimal flow briefly as well. So the way that you write this problem is that first you just input the data. Here I have two Excel files. I think these are all uploaded in the GitHub link. You can download as well. So I have a load profile, which is an Excel sheet that has my power consumption. And also I have the weather data, which would be the temperature, solar radiation, wind speed. Those are the ones that I need to provide so that I can basically get my wind profile and also get my maximum power from the solar. And then here's the part that I generate the wind profile. So here are the parameters of the wind turbine, cut in, cut out, and nominal wind power. So I have two wind turbines. One of them is 1.5, the other one is 3. And here is basically the formula that I utilized, and I showed you in my slides how you would basically calculate the output power of the wind turbine. Same for the solar. I will first read the data, and then these are the two equations that I have used to find the maximum power of the solar generation. You see some scaling factors as well over there, so that the data that we identified had to be scaled down so that we could utilize it for this problem. So that would give us the PV profile. These are the parameters of the conventional generations for the CHP. So those are the cost coefficients, max and min, ramp up constraints. We have another one for the diesel generator, and we have another one for the natural gas generator. These are the cost coefficients of the PV, wind, and battery, and then this is the up and down cost for the conventional generation. And then we have the battery storage constraints. Next we have the buy. If you remember, we had a C buy and C sell, which would be the cost coefficient for buying the power from the grid. And this is a dynamic cost because it's going to change over the day. So we put the buy and sell prices for buying and selling the power from or to the grid here. And then eventually we have some initialization. So if you are running OPTI, you have to initialize all the parameters. We are just initializing most of them with 0, except for the energy of the batteries. So this part is initialization, and this part is the one that we are running the optimization. So here, as an example, we are running for 24 hours. We have first, the problem that I showed you in my slides has to be converted to the standard form. That's why we have to find out AEQ and BQ. These are the equality constraints. If you take a look at the code, it tells you this. The first one is the load balance. This is the economic dispatch problem. And then I have energy of the battery and energy of the battery number 2. Those are equality as well. And then we have to define the inequality constraint, AX less than or equal to B. You can see the inequalities that we have here. We have the ramp down for the ramp up and ramp down for the generators. So we have 6 constraints over here. And then we had the bounds for the units, which was P of the unit should be between P min and P max times the status. And we had some nonlinear constraints. In this case, this was the status up and the status down, which was maximum of 0 and status minus the previous status. So these are the ways that you would implement that nonlinear constraint into your problem. And eventually upper and lower bounds. And here you have basically a type for your variables. Here you see C is the continuous, B is a binary. This problem is a mixed integer nonlinear programming. Therefore, we have to specify the type of variables for the problem. And eventually, this is the objective function, which is the cost. And we define the options for the OPTI. And eventually, we solve this problem. Once we solve it, we have to update some of the parameters. As an example, the state of charge of the battery every time has to be updated because you calculate the next state of charge. You have to replace the previous one with the one that you calculated. And here is we're just saving some values for plotting, and eventually we do some plots. Just want to show you some of the graphs that we can get from this. So this is, as you can see, we had 2 solar photovoltaic systems, and these 2 curves show you the power production of solar photovoltaic system over a course of 1 week. You see in 1 day, we didn't get much because this is realistic data, and that day was a cloudy day. These are the wind profiles. These are the maximum powers that we're getting from 2 wind turbines. This is the dynamic cost of buying and selling power to the grid. And this is the power consumption or electric power consumption within my system. And this is the economic dispatch results. So you can see over the course of 1 week, the red curve is basically my power consumption or the load. And the area graph, different colors show you the contribution of different units to the load. As an example, the blue one is the combined heat and power. The green one is a solar photovoltaic system. And then that's PV number 1. The blue one is PV number 2. And then we have battery storage units. We have wind. The light green one is basically the wind. And this shows you the contribution of every single unit in an individual plot. So this is the way that you would run the economic dispatch. We also have the code for the optimal flow in case you're interested in. You can take a look at that. So with that being said, I want to just pause for a couple of seconds or a couple of minutes and answer any questions that you might have.
Thank you very much, Professor Khazaei, for that interesting presentations. I hope everyone receive all this valuable information and you can learn a lot from this presentation. So we have a couple of questions from the participants. So the first one is one of the participants did the similar work for economic dispatch, but they use general genetic algorithm. And so he was asking what is the upside of using linear programming or nonlinear program. He also mentioned that there's a transmission losses that hasn't been accounted in the previous formulation. Can you comment on the impact on the output from that? Maybe I'll ask one question first.
Yeah, the first one is an interesting question. When we usually have a large scale system with many constraints and many decision variables, it's going to be hard to solve that problem because economic dispatch problem is a nonlinear problem. So if you're solving the nonlinear optimization for a large scale system, the conventional optimization packages or solvers might not give you the feasible solution. In those situations, you have the motivation to use meta-heuristic methods such as genetic algorithms or particle swarm optimization to come close to the optimal solution. But in this case, we are looking at microgrids. Microgrids are fairly small with a few components. So in those scenarios, you don't have a strong motivation or justification for utilizing meta-heuristic methods. And in those situations, even if your problem is nonlinear, you can lift it or convert it, relax it to a linear problem. An advantage of solving LP or linear programming is that you can find the globally optimal solution. You can guarantee that you can find an optimal solution for this problem. So that was the main motivation for doing LP. For the second question, Saskia, what was the second question? Was it transmission line losses?
Yeah, about the transmission losses, it was previously not accounted in the constraints.
Yes, so I didn't want to complicate the problem. As I mentioned, this was mostly designed for beginners or those who are not familiar with microgrids. In practice, when we do power flow, we have to account for the transmission losses, and that would add 2 more constraints for active losses and basically reactive losses within the transmission, which was ignored on purpose. But in practice, you have to account for those.
Thank you, Professor Khazaei. The second question is, in the case of generators, there is no constraint considering the lifespan depreciation of the generator. Do you think that the cost function from the conventional generators should be revised to address wear and tear and other problems leading to inefficiency in the power dispatch, specifically for the conventional generators?
Yes, that's absolutely right. And you know, when it comes to conventional generators, you have more constraints to be added besides the lifespan of the machine, which is going to be additional term added to the objective function. You can also consider time of use. For example, you can't just run the generator for five days uninterrupted. You have to shut it down so that it can rest. In those cases, you have to add those constraints. They call it time of use into the optimization. Again, I didn't want to complicate the problem by just adding so many constraints. So this was the most simple way of representing conventional generations. In practice, you can add as many constraints as needed, depending on the operation of your system.
So I have another question from the participant. So there are many uncertainties from the renewable energies, such as the photovoltaic or solar panel solar PV panels, what are the ways to incorporate them into the economic dispatch problem? I think you've showed it before. Can you mention several ways to integrate them?
Yes, so one of the ways that we have dealt with was on the forecast. So if you're predicting, now there are great tools for forecasting the available solar and wind generation. You can get pretty accurate results, and you can utilize those forecasts into your optimization. So if the forecast is not going to be strong or accurate, then you can account for the uncertainty within the bounds of your optimization problem. You can utilize methods such as chance constraint optimization. So you can provide an upper and lower bounds for the amount of uncertainty that you can have in your generation of, for example, solar or wind, and you relax or you convert the problem from this stochastic optimization to a chance constraint optimization so that you can solve. So there are many researchers working on this area. Again, there are a lot to explore. There are a lot to be done. Even when it comes to the battery storage, I presented the most simple way of incorporating the storage into the system, but you can have different types of energy storage. Nowadays in the power system, we are looking into hydrogen energy storage and how do we add that into the microgrid economic dispatch. So there are many things that can be done to account for the uncertainties in this microgrid economic dispatch.
Yeah, so thank you very much, Professor Khazaei. We have discussed all questions from this webinar. So before we sign off, I want to share another slide first.
Thank you, Saskia.
Thank you, Professor Khazaei. So before we sign off, for all the participants that have attended this webinar, do please register to our ECO-WES task committee if you think that this field is your interest. You can register to this QR codes for this QR code, and then we also have the QR code for the slides. We also share the links on the Zoom chat, and also the LinkedIn from our task committee. And for the next webinar, for our 3-part webinars, it will be led by Panda Power, and it will be held on February 2nd, 2025, from 10 a.m. to 11:30 a.m. Eastern Time. So register in our ECO-WES task committee and our LinkedIn so you can get updates to this webinar. Also, we have shared the links to the webinar feedback and slides for you.
I have a question. Sorry.
Oh. Yeah. Okay. Maybe you can ask one questions, and then we have to end after. Thank you.
Okay, thank you very much. So my question was Dr. Javad. So considering the high integration of a lot of base resources into the microgrids, are you looking at also modeling these resources, such as the EV charging stations, and then the integration of more vehicle-to-grid technology and all that?
Yes, that's a great question. And actually, we have looked into the electric vehicle to building, electric vehicle to the grid, and how you could integrate those into the economic dispatch. And we have, if you look, we have a paper on that topic as well. So when it comes to EVs, then you would add more constraints to the system. Specifically, EVs generate some stochastic nature to your system because you don't know when your electric vehicle charger is available. So that depends on the arrival time of your EV owners. For those, we usually, for example, model the arrival time using stochastic processes and then utilize those into the optimization. That's where you would need to, for example, utilize chance constraint optimization to simplify the problem and solve it. So there are many existing studies as well on that topic that explore integration of electric vehicles and charging stations or bidirectional chargers into the economic dispatch of microgrids, which I think you can learn more. But feel free to reach out to me. I can share the paper that we have published with you, and we have some sample codes as well if you need.
Thank you very much, Professor Khazaei. So I think And thank you, Anthony, for the questions. Please access the slides, access the link we have provided for the slides and also for the feedback on this webinar. Thank you very much for attending this webinar. We hope that you all consider this webinar as a valuable information and can learn a lot. Looking forward for the next future webinar. Thank you very much. Bye.
Thank you, everyone.
Thanks, everyone.